Good afternoon, everyone. Welcome to our second press conference of today. The initial title was Reducing Emissions, Renewable Energies, and Carbon Capture and Storage, but we had a couple of slightly last-minute cancellations, particularly the one by Alexandra Gormali. Actually, her press release is still attached to your press packs, but she unfortunately will not make it to. She did not make it to Vienna. She's ill and was unable to fly here. But we have Merce Labordena. She's a PhD researcher at the Department of Environmental System Sciences at ETH Zurich. And Jeffrey Bilicki. He's a professor at the Ohio State University in Columbus in the US. And I'll hand over to our speakers now.
Good afternoon, everybody, and thank you very much for attending this press conference. I'm Marcela Bordena, a researcher at ETH Zurich, and now I will present the last results of our current research. China and the US are the largest greenhouse emissions of all, with around 40% of all the emissions globally. In 2014, that means last year, the US pledged for emissions reductions by 28% by 2030 by 2025 compared to 2005 levels, whereas China, for the first time, committed a peak in emissions by 2030. To reach these targets, both countries will have to increase enormously the share of renewables investments. And both countries also, they have large potential for renewables, mainly wind or solar power, however the resources are intermittent. And then they will pose a great threat to grid stability. And therefore, technologies that are renewable, dispatchable, and also that can be built on land with a low use for agriculture, therefore would be highly valuable. Concentrating solar power, from now on CSP, with thermal storage, is a technology that englobes all that criteria. Therefore, our research question will be to examine the potential of a fleet of CSP plants to supply reliable and renewable electricity to the main cities in China and the US. We will analyze the costs and also identify the transmission corridors of large distances. And as mentioned, we will assess reliability, and reliability will be assessed from 2 points of view. One is to follow a demand curve, and the second one is to provide baseload power. This is the first scenario for China. So China will generate CSP from the best solar places that are basically in the Tibet. And the best solar places with the highest DNI is direct normal irradiation, are around 2,700 kilowatt-hours square meter per year. And our results show that an interconnected and coordinated fleet of CSP stations can provide demand following and baseload power to the big cities of China at reasonable costs. It is not only economical but also technically possible. Those transmission lines that you can see from the west to the large cities in the east have around 1,600, 3,800 kilometers. For you to have an idea, the largest HVDC link, that's high voltage direct current link in the world, is Rio Madeira, that is in Brazil, and has a span of 2,400 kilometers long. And also there are 3 gorgeous projects. In China, the largest link is around 2,000 kilometers. So these countries show that technically those projects are possible. This is the second scenario as well for China. So what if we diversify the supply, not only taking the best places, but the second best places. So we'll rely not only in the Tibet, but also in Qinghai. So in Qinghai, we have solar resources of around 2,100 kilowatt-hours square meter per year. And as you can see, the transmission distances to the centers of demand are much shorter, of around 1,200, 2,500 kilometers. That is of the same scope that the transmission link in Brazil of the Rio Madeira. The third and last scenario is for the US. So we see that fully controllable and baseload CSP electricity is possible in the US too. But mainly due to the monsoon, to the North African monsoon, though the weather is sometimes adverse, at many generation plants at the same time. So the overall cost may rise a little bit when demand following and to supply in baseload power. However, relaxing the demand following constraints give costs similar to the ones in China. Previous research in our group shows that by relaxing this constraint, the generation to follow the demand, say by 70% of the time, that for you to have an idea, a nuclear power plant works around 80% of the time due to maintenance and also due to stoppages, suddenly stoppages. So we see that when relaxing the constraints up to 70% of the time, costs to supply a summer peak load are around 15 cents kilowatt hour, and when meeting a winter peak load are around 25 cents kilowatt hour. And if we see also for compared from the previous slide, the cost in China, they are around 20 cents kilowatt hour. So in fact are direct comparable if we just relax a bit the demand following constraint. We have seen that the cost here in China are around 2 cents for meeting a demand, and to supply base load are around 9 cents. For you also to have an idea, the cost of a new coal power plant are around 9 cents. So in fact, the cost of the CSP are around the double. However, the experiences with technology learning, like the ones experienced with solar PV, solar photovoltaics, and wind, shows that increasing the construction of these technologies can bring costs down at an astonishing rate. So that's all for my side. Thank you very much for attending this, and please, if you have any questions.
Hello, I'm Jeff Balicki. I am a professor at The Ohio State University, where I have a joint appointment in the College of Engineering and in the School of Public Policy. I'm also on the Environmental Science Graduate Program faculty and on the faculty of the City and Regional Planning Program. As many of you know, there are a number of challenges facing our energy systems. Primarily, one of the challenges is to reduce the amount of carbon dioxide that's being emitted to the atmosphere. One way to do that is to deploy more renewable energy technologies, but the deployment of these renewable energy technologies also faces a number of challenges. In addition, reducing the water use intensity of the energy technologies of the comprised electricity system is another major challenge. When we think about renewable energy technologies, most people, I would say, would think about solar power and wind power. What we've been looking at more recently is using geothermal heat to combine the geothermal heat with CO2 sequestration in large, deep saline aquifers where you can simultaneously sequester the carbon dioxide but in hotter places and circulate that carbon dioxide to produce electricity. And the scheme that we've come up with actually also helps to enable the deployment of wind and solar technologies, which are limited by their variability. So the last few years, I've been working with Tom Bushek at Lawrence Livermore National Lab, Jimmy Randolph and Martin Sarr at the University of Minnesota, and Martin just recently moved to ETH Zurich. And again, like I said, we've been looking at using carbon dioxide that is intentionally sequestered underground to keep it from being emitted into the atmosphere. We circulate that carbon dioxide through the subsurface to pull out heat and then convert that heat into electricity. More recently, we've come up with a design for this geothermal reservoir that uses multiple working fluids, carbon dioxide and nitrogen and the resident brine. There's a lot of nasty water that's already below the ground. And we use that to to circulate both the CO2, the nitrogen, and the brine, all of which are pulling up heat, but also storing energy by pressurizing the reservoir. We have a design that uses concentric rings of wells where systematically pressurizing portions of the subsurface between these wells while we're pulling up fluids, both the native brine and the carbon dioxide or nitrogen that we've injected. This concentric ring design allows us to really manage the pressures, allows us to reduce the potential for CO2 leakage, and it allows us to reduce the risks of inducing seismicity. What we've been looking at is using this subsurface to produce and store energy. We can do bulk energy storage where we are basically time shifting wind and solar energy production by pressurizing the subsurface. We can then draw down that pressure as needed. So essentially we're taking wind and solar that when it's being generated and it's not needed, we store that energy underground. When we do need the energy or prices are higher, we can depressurize slightly and produce the electricity in the power plant. We've also added the capability to do thermal energy storage. One of the problems with accommodating wind and solar on the electrical grid is that the existing baseload plants have to be able to shift down in order to accommodate that electricity. And conventional baseload power plants such as coal or nuclear, they don't want to shift down. They run pretty constantly. So what we are doing is taking the heat that is being generated by the coal or the nuclear power plant and preheating some of the fluids that we are injecting. And that allows us to not dispatch the coal electricity or the nuclear electricity, but rather to dispatch the geothermal heat and the wind and solar that has been time shifted so that we can follow demand. We have a video at www.energypathways.org that explains this process in much more detail. This was created by a Master's of Fine Arts student who I worked with for about a year. This was part of his thesis and is fit for public consumption. I'd like to thank the U.S. National Science Foundation, the U.S. Department of Energy, and the Institute for Renewable Energy and Environment at the University of Minnesota for funding that they've provided. And there's a long list of publications that we have related to this. And with that, I'd be happy to answer any questions.
Thank you very much for very interesting talks. And we'll now open the floor for questions. Please say your name and affiliation and who the question is for.
Hi, I'm Lucas Laursen. I'm here for the AGU's EOS newsletter. What's the largest physical demonstration of this system that exists?
That's a tough question. There are a number of CO2 capture and storage demonstration projects throughout the world. Our particular conception with these concentric rings has not been deployed, or there's no demonstration projects in it. Right now, it's all computer simulations. There are some projects that are looking to tap into existing CO2 sequestration demonstration projects, as well as to look into how to pull the heat off of oil when it's being produced for enhanced oil recovery, when CO2 is injected. We have a number of sort of staged projects that we would like to do, one of which would ultimately be to drill some wells, although we haven't gotten there yet.
Very quick follow-up. What will it take? I mean, what kind of investment would you need? How long do you think that sort of thing would take?
Yeah, so part of the reason this idea came about with the concentric rings of wells is that, in the U.S. and some other places, we're hydraulically fracturing a lot, and we can directionally drill. Those wells cost upwards of $10 million to drill. So we would need a fairly substantial, to do a large-scale demonstration project, we'd need a fairly substantial amount of money. What we have been more recently looking at in our computer models is using just normal vertical wells and sending them out in a circle. That might reduce the cost by 2/3 or so. The major thing that we need is on one hand access to pore space, permitting. This actually. I'm trying to figure out how this would be permitted because it's both geothermal and carbon capture and storage. In the U.S., we have the underground injection control program, which really looks over subsurface injection. Right now, we expect that there will be one of these EOR-like projects within the next few years, but probably much longer before we actually get the concentric rings to do it.
Thank you very much. Are there any additional questions?
My name is Milan Ilic, and I live in Vienna, reporting for the leading Slovenian daily paper Delo. Just one question to you, Professor. As your colleague has written, is your, solution of storaging of carbon dioxide non-plus-ultra solution, or is it just temporarily, which enables the society to do business as usual?
Which colleague was that you're referring to?
I mean, here, because we get in papers that it is, storage, actually we are dealing with a byproduct which we do not need, or the earth does not need in excessive quantities. And is the storage of carbon dioxide a long-term solution, or you think until we find out something, better?
Well, I have a few answers. One is that we would like the CO2 to be stored for a long time. In terms of it being a solution that we do for decades and decades and so on, the basic conception is that this is intended to bridge, the CO2 storage is intended to bridge to future energy systems that are comprised of larger penetrations of renewable energy. And part of the way that bridge works is by increasing the costs of producing power that emits carbon dioxide by having to add capture equipment and pressurization to pipeline it and so on. That levelizes the playing field with other energy technologies. And like Mercedes said, they were roughly double, dollars per megawatt hour, roughly double for the concentrated solar power that they were talking about. The estimates for CO2 capture and storage could increase electricity prices roughly double them, depending on a number of circumstances. So I would like to think that it would be a medium-term situation. The big driver is that we really need to reduce the amount of CO2 that's getting in the atmosphere. And that CO2 is not just coming from coal-fired power plants. There's a lot of industrial activities, cement manufacturing, ethanol production, and so on. So adding the CO2 capture and storage can be deployed actually on some cheaper options than the electricity system, but still still reduce overall. The climate doesn't care where the carbon dioxide came from, but the energy system does.
Okay, thank you. Are there any more questions? If not, we'll finish here. Thank you very much. You're welcome to approach our speakers after the press conference. We have 4 press conferences for you today, including one on the latest results from the ESA Rosetta mission. But we'll be starting at 10 with a different press conference on greatest hits, water in social media, smartphones, GPS, and popular music. I'll see you tomorrow, and if you're interested, there is a great debate today on the impact on global geoscience of accelerating Asian research. It's at 3:30 p.m. in room Y1. Thank you. Bye.
Thanks.